Hello.
Oh, hey, Theodora.
Hello, Theodora. So can we start now?
Sure, I think we have everybody.
Okay. Okay, start. So today we're going to talk about the chapter 19, the product topology. And in this chapter, we're going to define some more general Cartesian product on the topology. So first, let's consider the Cartesian products on x1 all the way to xn, and the infinite products x1 to x2 to infinite number. Okay. So there are two ways to proceed the topology. The first one is we call it the box topology. It takes as basis all sets of the form U1 to U2 and all the way to UN for the first type, and then the infinite number for the second type. Like the U is the open set of X in each alpha. And the second type is the product topology. We take as basis all sets of the form this thing. This is the projection map. So it means there are some, sorry. The typical basis element B in the box topology and product topology are different because this projection map is only can only present from y1 to yk, and there's no restriction on other values of yi. So this means when the topology are finite, then these two topologies are the same, but they're different in infinite products. Okay, I will talk more details later. First, let us learn some general notion of the Cartesian products. The first one is the J tuple. It's very similar as we have already learned. We denote x alpha as the alpha coordinate of x, and then we have a. Can I write here? Okay, and here, I don't know how to pronounce this thing. It's defined as the Cartesian product of A alpha, the index family of sets. Okay, so I think this is all we need to know. Next page. Wait, what happened? Okay, so the definition of box topology is basically where we find an open set U alpha in every x alpha for alpha and j. And then topology generated by the basis is called the box topology here. And first we need to verify whether it's a topology or not. So first, I will write here. Here first, this product itself is a set. Itself is a set in the base, and the second, the intersection of this basis are also in basis, right? Because U alpha intersects with V alpha is also an open set in X alpha. So now we prove that this thing is a basis element. And the definition of basis. Oh, sorry.
Can you
Yes.
stop for a second and give us a moment? Because I think there's a lot of definitions going on and we need a bit of time to read it all.
Oh, right. Okay.
Oh, okay, gotcha. Well, or maybe somebody else wants to have a little more time.
Okay. I'll wait for a minute. Let me explain it again if anyone wants it. Like for the first condition, every element x in here, I don't know how to pronounce this one, is in some spaces element, right? And then this is, we can write it like in easier form. Here B1 intersects with B2 can be described as B3, or and it is the condition, two condition of basis, of being a basis element. Okay, and then we'll go to the next slide. Oh, sorry, which one? Here. Oh, so here's the definition of the product topology. It's very similar to the box topology, except that the U alpha is oh, okay. Let me read it again. Like we first define the product mapping pi beta as the function assigning to each element of these things, it's beta coordinate. So it's basically a projection map. So this S beta is denoted as a collection of such things, where U beta is open in X beta, and when it's not beta, for example, if it's other index, the set is like X itself. For example, U beta intersects times, for example, X1 and then X2, and then many other. So this S is denoted as the union of this collection as this collection. And the topology generated by this subbasis S is the product topology. And this topology on such things is the product space.
Okay, sure. Just so basically to give it a physical like kind of intuition. So what you're saying is that there is an open set UB, and you're just taking all possible like call it vectors or whatever, like vectors which have the B coordinate to be from this open set, right?
Yeah, yes.
Okay, so basically if you visualize it, you just take an open set and then you take everything else in possible directions, right? So that takes like a part of the space, right?
Yeah. All the other spaces except the one we have already taught, except the one we have restriction, like the U beta. Okay. So now we will verify that S is really a subbasis for the topology. Oh, wait, do you need more time to read this definition? If no, I'll continue.
I'm good, but maybe somebody else need. Guys, you can say if you're fine and we can go.
So, does anyone have any question about this definition? Oh, if no, then I'll continue. Wait. Oh, okay. Oh, I forgot there's a question here. How to verify that S is really a subbasis for a topology? I have a little like clues here. So I'll give you a minute to think about this question.
I forgot. When we say sub-basis, the sub-basis is basically like a usual basis, but it's supposed to be finer than another basis, or what was it?
A subbasis is a topology on X, a collection of subsets of X whose union equals X.
Okay, sure.
So the subbasis, the intersection of subbasis is a basis. Like the basis can be written as the intersection of some subbasis. Yeah.
Okay.
And this might be some clue.
Well, first, I guess we can always take, say, a union of open sets that look like UB, whose union gives us XB, right? And so that's how we can like cover an entire XB. And so
Yeah.
I guess you can just do the same, but kind of like show why P inverse XB would be covered by would be covered by union of P inverse B UB and stuff, right?
Right. And the more easier way to do this is to exactly take UB as XB. Like XB itself is an open set in XB, right? So this projection map is actually this Cartesian product here. So we have the now we have proved that the basis can be written as like as a subbasis.
Well, I'm not sure why does that, because like I definitely see why like the P inverse XB would be a Cartesian product. I think that makes sense just because of the definition. But then what do you mean by that it's evident that it's a subbasis? Maybe I don't understand your definition of subbasis again.
Wait, let me check my notes again.
Because like I think like the first equality, like totally agree that just goes from definition, but I don't understand why that is in the S, like.
So we only need to prove that there are sets in this S, which is a basis, sets in S which can be written as a union of subbases.
So yes, but like, how does a Cartesian product help you to show that there is a union?
Like here, this map can be written as this function can be written as x1 to like you get an idea here, x1 to x2, and then x beta or whatever. It's exactly this one.
No, yeah, I totally get why quality holds, but I'm not sure how this union offsets come into the play. Like, I totally agree that, of course, like P inverse XB would be a product, a Cartesian product, because of the definition, right?
Yeah.
Because it's like the whole space, basically. But then, why is it a subbasis?
So Holly, what is the definition of subbasis, or how can we check some set is a subbasis?
Like the definition is the collection of subsets of X whose union equals X, right?
Yes, so, but here you may get some wrong notation here, which is why it becomes a little bit confused.
Okay. Sorry, let me check it again.
So you want some subset of a set such that this collection of subset contains this whole set, right? This is a collection of subset you want.
Yes.
Now you can see that this kind of pi inverse, pi beta inverse, right? This kind of thing contains this whole set.
Yeah. Yes.
Which maybe you don't really want to name it as S, right? Because you also call it the this subbasis as this kind of another S, right? So what do you want to name your whole set? And what do you want to name your collection of this whole set? So first, if you want to define a subbasis, right, it has to be the collection of subset of some set. Right? Am I right?
Yeah, right.
Then what is this set? What's the name of this set? Subset of some set. The subset of what set? What is the name of that set? You have to give me a name, right?
Yes. Is the Cartesian product X alpha?
Yeah, it's pi everything, right? You multiply everything. This is, well, maybe you can call this another thing. This with this name as let's call it maybe capital X at this moment. Okay. And then if you want to show this kind of pi, little pi beta inverse X beta, this kind of thing forms a subbasis, right?
Right.
Then you only want to say that this X is one of this kind of thing. X is of this form, right? X is this kind of form, right? Then you are done. Am I right?
Yeah.
So you show that, okay, X, your whole set, is actually this form. It's of this form, which is why, okay, it is actually a subbasis. Is that correct?
Yeah, and
you use S as this collection of subset of X, right?
Yeah. It's a collection of X. Okay.
So then you have proved that it's actually a subbasis. So if you want to show it's a subbasis, in general, you only want to show that, okay, this kind of collection, if you take the union of this collection of subset, you get everything. So this collection can cover every set, every subset, right? It can cover everything, every element of your whole set. And now you show that, okay, there actually exists an element. There exists one thing in this collection such that it's a whole thing. Then of course it's the union of this collection of subset can be seen as everything, right?
Yes. So I don't need this one. This one here.
Well, what do you don't need?
Here.
I mean,
I guess
you can actually you could have that because it just means that this in this S you have this X as well of this form, right? You have X as an element in this collection of set, so that's fine. I mean.
Okay. Yeah, thank you.
Yeah. To say it's a little bit twisted, but yeah, this can be solved by giving this kind of set and collection of set a good name. Otherwise, it's really confusing. I agree.
Okay. Yeah, thank you. Is there any question about this page?
I didn't get what happened. Can somebody shortly explain so YS is a basis?
Like we need to prove to prove it's a sub-basis, we need to prove that this how can I write here? Like such thing, we call it X, which is the topological space. We to prove that this pi here can cover, or its collection can cover X. But now we have already proved that it is equal to X, so it's a sub-basis. So here, this is a sub-basis.
Okay, so sub-basis intuitively should just cover something. And
yeah.
So if it equals, it covers. That's what you mean?
Yeah, I think so. And if it's not equal, we can also have like U1 in beta, U beta 1, for example. And then with U beta 2 equals to X beta, then it's also a sub-basis that can cover X, right?
Okay, sure.
I think that's the definition of sub-basis. Is there any other question? Then I'll go to the next page.
Yeah, maybe I should just say one more thing. For the idea of sub-basis is just it's very simple. You want some kind of subset is a sub-basis. Well, it's some kind of collection of subsets to be a sub-basis. What you need is very simple. For instance, you have a set. It contains a lot of elements. Then what you want is some subset such that all this subset. There is nothing you don't discuss, right? There is nothing that not be covered by this information. That will be enough, right? And then if every element of this set can be discussed, whether it is in which subset it is in, this kind of collection of subset, then then it is a good sub-basis. Otherwise, this point is not in any subset of this collection of subsets, then it will not be a good sub-basis. It will not be a good collection, then it will not be a sub-basis. Okay. Anyway, yeah. Well, if you still get confused, please try to reread it and see what's the idea of this subbasis. Okay, it's very general. It's kind of a very general idea about the collection of subsets of a set.
Okay, then we'll go to the next page. Oh, okay, here. Here we'll compare these two bases on the box topology and the product topology. So if we find, let's consider the product topology, the basis of product topology first. So the collection of the basis B consists of all finite intersection of the elements of S. And if we intersect elements belonging to the same set as beta, which this beta is an index, then we get nothing new, right? Because this U beta intersects with B beta is also an element in the space X beta. Like this, beta here is an index. And so if we want something new, we need to intersect with elements from different sets as beta, different set as beta. So the typical element of the basis B can be described as the finite number of beta 1 to beta n, and then with other for numbers that are not in 1 to n, there are just x, like for example xn plus 1. So this notion here can be also written as U beta 1. Oh, this is too difficult to write. All the way to U beta n, and then times xn plus 1 and n plus 2, or all the way down. So it only restricts the indexes we have defined here, 1 to n. So the typical notion of the basis B here is, oh, sorry, can you see here? It's written in this form, where U alpha denotes the entire space X alpha, if alpha is not in beta 1 to beta n. Oh. I'll give you maybe a minute to read this whole pages.
I'm not sure that's only my problem, but I can see below the part where V equals to the Cartesian product of U alpha.
Yes.
What is written under that? Because Zoom has this thing when it cuts the image. So I think part of your image is not there. Can you read the last line?
Oh, the last line is where U alpha denotes the entire space X alpha if alpha doesn't equal to B1 to Bn, B1, B2 all the way to Bn, beta n.
The entire space X alpha where alpha is not equal to any of the B's. Interesting. So oh, I see. So are you basically saying that when we take the P inverse of U P1, it just basically gives us like that like open subset UB multiplied with a Cartesian product by in all directions by like entire spaces in all directions, and it happens for every coordinate. And then when we take intersections, then you just get a Cartesian multiplication of those open sets because you restrict it to it. But then in the coordinates where you don't have any restrictions, it just stays a whole space. Is that like the idea you're trying to imply? Okay. Okay. Theodore, Zikan, you're so silent today. Are you guys fine? I'm also lagging a little bit. Maybe what would really help to guys is a good visualization of that. Because I think when you write it like this, it's really technical. So maybe we can try to draw something and like show to guys how it works. Would you want to try?
Oh,
I can help you draw if you need help because I have.
Like my internet has some problem.
Oh, no worries.
Now it's back to normal. Hope it's back to normal now.
I was just saying that I think guys have problem understanding that part because it's the first time they see it. So maybe we can try to draw it and visualize it, and then it will be easier when we draw it, right? Maybe we can try that.
Oh, okay. I can draw this. What happened? Wait.
Sure.
Oh, I can draw it. If it's a 3-dimension, like the 3 Cartesian products. Here, this is the X. Oh, too bad my drawing. This is Y, and this is the Z coordinate. And if we set U beta 1 in the X coordinate and Y coordinate. For example, if we have X and little square here in X or Y, and then the coordinate on Z is not restricted, so we can get all the points at Z, like here. So it's basically a very, very long.
Wait, I think it's not a block though. I think it's a kind of like I guess a space more, because if you, for example, have let me try doing that. So I think, for example, your UB1 can be this.
Yeah. Mm-hmm.
And then what you're trying to see is you're trying to say B1 inverse UB1 is just everything that gives you B1 in this coordinate. But then you don't have any restrictions on here. You don't have any restrictions on here, right? And so together it kind of creates like a multiple layered plane, I guess. It's not even a plane, it's just like a subsection of the things. Like it takes plane here, and then it planes through here, and then it planes through here, and then it planes through here. But both in Z and Y directions, right?
Yeah.
So messy. Sorry.
So what I'm drawing is if we have 2 limitations, both on X and on Y, then we have a very long, like a space. And here is U beta 1, and this is beta 2. Right?
Theodora at second, does it make more sense if we draw it, or are our drawing skills really bad?
Oh, drawing is too bad.
Yay, it's better. That's great. Maybe you can even try to be like, so if that's your Q, right, then you want to have a projection here. This would be your UB1. You want to have a projection in here. So that's like your UB3. And then a projection in this direction, right? And that would be your UB2. If that helps more. So basically you're trying to see like these things are basically the projections of the entire result. And so together, when they take intersections, you get this whole thing restricted by n things. So it's an n-dimensional kind of cube. No, not cube. A rectangular kind of figure, whatever.
Yeah.
Should we go on?
Okay, then we can go on. Okay, so next page. Okay, so now we talk about the theorem 19.1. We compare these two topologies. As we can see on the previous page, here, if the product is finite, we can take this n all the way to cover every j we have. Then the topology on the product topology can be the same as the box topology, right? Because everything is there, the open sets in X alpha in the index set J, in the index family. But when it is when it is an infinite set, they're different, and because the box topology, every base in the box topology has like the open set here. When it's infinite, then the n cannot. When it's bigger than n, for example, n plus 1. And for the product topology, there is an x, but for the box topology, is u. Like u is smaller than x, right? So the box topology are finer than the product topology. Okay. Oh, my definition is so. Okay. So it's basically when they're finite, they're the same, but when it's infinite, or when they're infinite, the box topology are finer. So generally, the box topology are finer than the product topology. And we go to 19. Oh, do we have any question about this?
Yeah, can you give just a second so we can like read it?
Oh, okay.
Okay, I'm a little bit confused over, so why does it have to be only finitely many values of alpha?
Finitely many. Oh, because we only call the indexes in the previous page we have here. Like index here for I is only to 1 to n. This n is not an infinite number. So we cannot cover all the infinite number. Right.
Wait, actually no. But you don't have n here, right? Because I think what you were explaining there and here are different sets of numbers, isn't it? Because I think your j doesn't have to be finite, right? So I'm not. So like, yeah. Or yeah, I just don't see why. Like, why can it be like infinite? Because I think infinite definition would still make sense, right?
Well, just as a hint, so what is how you can get a topology from a subbasis or from a basis? And there are something. There is one operation you can do it infinitely many. There is another operation you can only do it finally.
I think with open sets, you're only allowed a finite intersection, right? But you're allowed an infinite number of unions. Right?
Exactly. So which is why the product and the box topology are different. And product topology, as you said, is much easier, in some sense, easier than the box topology. And well, sometimes easier means better, okay? Which is why sometimes we even, well, actually, in most of the case, we prefer the product topology instead of the box topology. This is kind of like the simplification of this kind of problem, because when you have this infinite many product or infinite many things, then, well, sometimes it will be pretty complicated. You don't really know what is the structure of something, but if you try to deal with this kind of thing by saying that, okay, infinite many, it doesn't mean anything. It just means that, okay, there might be any length of something, of non-trivial something, like only finite many, only finite length, well, only finite many, well, spaces that could be non-trivial. Other than this kind of spaces, well, they are just trivial. Then the problem may becomes easier. Okay, so this kind of topology just trying to see, it's just trying to see this kind of infinite many product space as some collection of, if you try to see it as a sequence, it's just trying to collect all this kind of sequence such that after finite many terms, or eventually this sequence will become trivial. Okay, eventually everything becomes trivial.
Wait,
so this is our idea.
So basically, because B was defined as an intersection of open sets, we want the B from the previous slide to only have finite intersections, right? And so that's why the box topology, which depends on definition of B, has to be finite, right? Like
what do you mean finite?
Like finitely dimensional, like J has to be finite.
Not really. It's not about the finite dimension or not. I think it's something else. I should say it should be seen as something else. For instance, you can just imagine, well, if you are in R2, right? Then this kind of thing, the box topology and product topology are the same. But how can you get this kind of the equivalent of these two things? Okay, the box topology is you just choose a basis as each boxes, right, of R2, each rectangle on R2, right? This is box topology. But for this product topology, you try to take all this infinite cylinder or infinite strap as your basis and take the intersection of them. Okay, this is the idea of two different kind of subbases. And then, okay, this is R2, so you can see that they are the same, because if you try to see the box, then, well, of course, it's kind of the intersection of two infinite length strip. But then if it is infinite dimension, it just means that, okay, you may have some, well, if you try to see it as Rj, right? R, you do the product infinite many times. Then for infinite many times products, then this kind of a box topology means you could have an open set such that it is an open interval times an open interval, A1, B1 times A2, B2 times A3, B3, and so on. It's just the product of all the open intervals. But for this product topology, it cannot have this kind of set. It can only have those kind of sets such that something A1, B1 times A2, B2, but after some finite number, capital N, all the rest of this kind of product must be times R, okay, times everything.
But why?
Otherwise, it cannot be generated by this subbasis. Because if you try to take the intersection, if you try to take the finite intersection, right? If you try to take the finite intersection, then you can only get finite many things, this kind of open interval, finite open interval. Other than this finite many things, other than this finite many U alpha, other than this U alpha, everything else are just X beta, whole space. Right? For instance, you have this, you may have this, this product space as, this kind of thing could be seen as B. Or you can think, okay, if you want to have, for instance, you have some kind of A comma B, 0, 1, okay? 0, 1. If you think this X alpha equals to R, everything equals to R. Then let's say, for instance, you want to take pi inverse 1, 0, 1. Okay, so the first R, you take the open interval and take the inverse of this projection. Then what you get, one of the subbases is 0, 1 cross R cross R cross R cross R, infinite many R. Okay, and then this set, this is one of the subbases, and this set you can intersect with another set which might be R cross 0, 1 cross R cross R cross R. So the second place becomes 0, 1. Okay, if you take this 0, 1 cross R cross R cross R, intersect with R cross 0, 1 cross R cross R cross R, you take the intersection of them, then what you get is 0, 1 cross 0, 1 cross R cross R cross R, right? Then you get two finite open interval. Okay, and then if you take another intersection, you may get, this kind of product may contain 3 finite intervals. But other than these 3 finite intervals, other than these 3, everything else are just the whole spaces, whole R. Okay, which is why eventually you can only get finite many things, non-trivial. Other than this finite many things, all the other product are just multiplied by the X alpha, the whole space. So this is a difference. This kind of thing are the only thing in this, this product topology. But for box topology, you can have everything to be 0, 1, cross 0, 1, cross 0, 1, cross 0, 0, 1. Everything is just a 0, 1. Okay, if you want, you can think it's infinite many dimension things, like R infinity, this kind of thing. Well, maybe I should let you adjust. We'll try to digest it and see whether you can get it or not.
Okay, so basically this intersection can only be finitely many intersections, right?
But I think what you just stated is different from Professor what you stated. I think Professor was saying that you only have finitely many non-trivial ones. Because of a reason I still don't understand. But then I think your statement is that you only have finite dimensions in the box topology, because if you have more than finite dimensions, you like the intersection may not be open. Wait, but why do you want B to be open? I still don't get it.
You mean the basis B?
Mm-hmm. Oh, it's a basis. Okay, sure.
Yeah. So the box topology here, the definition is like all alpha and J is we take it the U alpha, the open set of X alpha for every J, for every alpha and J. This J is not, it doesn't tell us whether it's infinite or finite. So, okay. And you have other questions about this page? Okay, it's not this page, it's this page. 19.1. And I'll go to the next page. So next page is a theorem. It's very similar to the theorem we have already learned in the chapter 15 or 16 in topology X times Y. So I'll give you maybe 2 minutes. You can think about this. The proof is very similar as the one we have learned. I'll read it for you. Suppose the topology on each space X alpha is given by a basis. Then the collection of all sets of the form the Cartesian product of B alpha, where B alpha is in the basis for each alpha in J, serves as a basis for the box topology on the topological space. And it's the same for the product topology, except this alpha is for finitely many indices alpha, and then B alpha is equals to X alpha, which is the whole space for all remaining indices. And so basically it's just, we need to prove whether this Cartesian product of B alpha is B alpha here is a basis, can serve as a basis for the Cartesian product topology.
Okay, so basically the Cartesian product of bases is also a basis, right?
Yes.
Well, maybe let's do it together. Definition of the basis, I think, is first, it has to cover all elements, right? It has to, there always should be one basic element which contains X from the thing. And I guess for the product topology, it's more or less obvious because for any element x. Yeah, I guess for like any element x, you can always look at the coordinates and say that this coordinate is contained in this basis element and this coordinate is contained in this basis element and stuff, and then you just take their cross product, and so you obtain a base element which is there, and it has to be only finitely many, and this is alpha, for which B alpha is not trivial because, well, any element is contained in the X alpha, so it's even easier. So I guess the first part is fine. I can write it for people. Theodora, can say something, please. I don't know if you guys are there or not. If you're following or whatever.
Can you write here? Or you
Sure,
cannot write?
I can. Yeah, I can write. I just kind of like I don't know if the or Theodora are following or if I have to repeat stuff or whatever. So I guess we can try doing, say, we want to cover any x in the product topology, x alpha, right? And so we can write it as x is equals to x1, x2, and whatever. And so basically it can be like for so x1, for example, would be contained in some basis element b1, for example, I don't know, and then x2 would be contained in like b2 whatever, so like basis element of b2, b1, and then we can continue doing that, and then for others we can just do like, I don't know, for all n bigger than some n, we can just say xn is in the like x n, like the big X, because it has to contain all the elements. So basically then we take this and we get b1 cross product, b2 cross product, whatever, xn. It would be a basis which contains x, right? So I guess that should work, probably.
Are they the same as the basis we have already defined?
They should be, but I forgot the definition.
There's at least one basis element B containing X. Okay, then so my answers like different, my approach is different from yours. Oh, sorry, I just delete yours. Sorry.
No, I deleted mine. It's fine.
Oh, okay. Now I'll show you my approaches. Wait, what happened? This computer sucks. Oh, here. So I'll write it here. We're basically I'm basically proving this new form of basis is exactly the same as the basis we have defined in previous pages. And this B here, like the basis we have already defined, is written as the Cartesian product of the U alpha. If it's for the product topology, some U alpha is equal to X alpha, when the alpha for finitely many indices alpha, and for the remaining indices, the U alpha is the X alpha. So they're this form. This B here is this form, and we need to prove that B is contained in B pi or B prime. Here, because B alpha itself is an open set. It's an open set because B alpha is a basis. So this product is also open in the box topology and the product topology. So this B is this B is contained in B prime, because we can define B prime as B, like the intersection of like the union of B, because B is a basis, right? And this is an open set. Open set can be written as the union of some basis, right? And then for the other side, for the other direction, we have this Cartesian product of U alpha equals to this. I don't know how to pronounce this one. Like the union of the Cartesian product B alpha, where B alpha is in U alpha. So this Cartesian product U alpha is the basis element we have already defined. And then since
By the way, the name, well, the way you pronounce it is correct. You can say it is a Cartesian product of.
Sorry, like my internet is broken again. Can you hear me?
I can hear you, Holly. I think your internet is fine.
Oh, okay. So so can represent it as a union of some basis element defined in the theorem, like so B prime contains B, if you cannot see here. So we have already proved the second direction, so they are equals. Okay. Do you need more time to read my proof?
Sure. Well, actually, give me a second. So what you're doing here is you're are you basically saying that because I get an impression that what you're trying to prove is that one topology is like finer than the other, right? Which is great. I'm just not sure if that actually a proof that the basis elements are the ones that should be. Are you sure that this is a picture from the right proof? Because I'm go on.
Because it's already equals, and this B is the basis we have defined. So I think they are the same. So it can serve as a basis.
So I think what you're saying in your proof is you take a basis in the box topology, right? And then you're trying to prove that it's also a basis for the product topology, right? But,
I'm doing the same things again together. Like it's both in box.
Yeah, no. I don't have problems with your proof, but I think what your proof does is you're trying to prove that the basis of a product topology is equal to the basis of the box topology. But I think what the theorem was actually asking is if you have a base in one space and then you have a base in the second space, you have to prove that a cross product of those bases make a base in the combination of spaces. But this is, I think that what was asked, right? I hope I'm not mistaken.
Like it's my writing problem, because I'm too lazy. I just write it in the same page. If you delete this part, it can be a proof of the first question, like the box topology. like this B prime here is this one. So because this the proof are the same for these two topologies, so I write in the same page, in the same proof.
Sure, I guess the proofs are really similar. I'm just okay, doesn't matter. I just think that like what you were trying to do is to prove a different theorem. I think you confuse the theorem or the proofs, I guess, because there is a theorem like that later in the book, which are you proving right now. And basically you're proving that product topology and box topology are like kind of like equal because they are, one is finer and then another is also finer, so they're kind of equal. But I think what this theorem is asking is if you have bases in different spaces, that you can combine them together to obtain a new base which has more dimensions. So basically, if you have a base in x direction and then you have a base in y direction, then you can take cross products of those bases, and their cross products would be a base in the plane, right? So I think that's what the theorem asks. But I mean, your proof is still correct. It's just correct for another theorem, I think.
Oh, but if it's already a like your what you're saying is take one, like for example B1 cross B2, right? And then it's already like a basis in the plane. So why can't you just say it's equals to the basis? Like is it equals to B?
Oh yeah, because I mean the fact that like a multiplication of bases is a basis is not obvious, so you have to prove it because it's a rigorous theorem.
Oh.
But yeah, I mean like your proof is beautiful. It's just for another theorem, I guess.
Oh. I don't know. Probably you're right. Oh.
Well, I guess we can just do it as an exercise and go on. Like don't mind it.
Okay, then yeah, this is just an exercise of the textbook. The textbook doesn't give us any proof of this theorem. So I don't know the right answer of this.
By the way, there is a website with proofs. You can search them up.
Oh, there are too many exercise lessons. Okay, then like, should we go to the next page? Okay, then I'll go to the next page. Proof of, as an example. So we consider the Rn, which is the R cross R all the way to R, n times R. R all the way to R, and there's like you get my idea. So the basis for R, the standard topology consists of all open intervals in R. So by theorem 19.2, a basis for the box topology and the product topology is the set of all products of the form this open interval cross another open interval. So this standard topology on R, so this is the standard topology on Rn. And because this is Rn, it's not finite, it's not infinite. So the box topology and the product topology are the same. But notice that this example can be modified to find basis for the box topology and the product topology. Here, what does it mean? Oh, I don't know. So we just need to know that. Sorry.
What didn't you know? I didn't hear your question. Sorry.
Like no, it's just a little note here, like this. the standard topology on Rn can be written as the box topology or the product topology. They're the same.
Sure.
This is what the example wants to show.
Sure. So basically, then I have a question. So for when we have our, say for example, three-dimensional space, in three-dimensional space, product topology and box topology have the same basis. That's why they're equal, right? So what happens when you have like here RW? So basically what happens when you have an infinite dimensional space?
Then the box topology are finer than the product topology. Right.
Is that because you're allowed to have limitations infinitely many times, right?
Yeah, yes.
Okay, sure, yeah. Makes sense. Thank you.
Yeah. Okay. So it's just a little note. All you need to know is this one. They're the same as in the box topology and the product topology. Okay. So I'll go to the next slide. Oh, happened. Oh, it's the theorem 19.3. And if let A alpha be a subspace of X alpha for each alpha and J, then the product of A alpha is a subspace of X alpha if both products are given the box topology or if both products are given the product topology. So there are two things to prove, but they're very similar, so you can just prove one, anyone. For example, the box or the product. Do you remember what is the subspace topology?
Was it the intersection of a topology with an open interval? I'm not sure.
Like if Y is a subset of X, and then the subspace topology on Y is Y intersects with U, and this U is an open set of X. Yeah, just like this. Oh.
Okay, actually I have a question here. So like, but in the product topology, you're not allowed to have infinitely many limitations. Then does it mean that your cross product is only finite?
Cross products. Cross product. Finite. Oh no, it can be infinite. But when it's in the remaining indices, when alpha is not in like for example alpha is bigger than some, like it's not in the indices, we can have U alpha equals to X alpha. Like the A alpha is A alpha itself. Like the subspace of A alpha is A alpha itself. Because A alpha time intersects with X alpha, right? So it can also works for infinite number.
Okay, so basically you're saying that because its intersection was specific one interval, we can have as many limitations as possible because we don't touch bases at all?
Touch bases? No, we still need to use bases here.
But then if you need to use bases, then shouldn't we make sure that only finite number of A alpha is like strictly less than X alpha?
When it's not for some A alpha, how can I write here? What happened? Wait, let me write here. So for some finitely many numbers in the product topology, this open set in the subspace is U alpha times intersects with X alpha, right? But when it's for the remaining alpha, we can have A alpha intersects with X alpha. A alpha intersects with U alpha or X alpha or X alpha. Is it? Let me check it again. U alpha. Oh, sorry. This is A. This is A alpha.
I'm sorry, what is your U alpha?
This U alpha is an open set in X alpha. I should have said it earlier. It's an open set here in X alpha. And this A alpha is this one. It's for finitely many alpha. Finite. Alpha equals to like many. Finite. And then these are the remaining part, which is exactly equal to A alpha. Because this X alpha is an open set, right? So these are also open in the subspace topology.
Okay. Well, then I kind of have a question. So basically, A alpha is a subspace of X alpha because A alpha is just X alpha intersect some open set, right?
Yes.
And then basically you're saying that cross product of A alphas is a subspace of X alpha, right? So basically you would have to show that cross product of A alphas is equal to intersection of cross product of X alphas with some set, right?
Yeah.
And so, yeah, so it basically means that you would have to have like a multidimensional intersection, and I don't think we ever defined it.
Multi-dimension, but like this one is, I have already did it here. Right.
Yeah, sure. So basically what I'm saying is you did it for alphas. So basically you wrote a cross. How about, do you mind if I write here? Because I can explain it well. So basically what you're saying is cross product of A alphas is equal to say whatever A1 x1 cross product A2 x2 blah blah blah, right? So basically you wrote it like this using this. So from here this follows this, right? But I think to prove that this is a subspace of this, you have to show that this is equal to this intersect something. So I think that's what definition of a subspace is, right? But I'm not sure how do you do a definition of subspace in multidimensional thing because this is not one dimensional thing. It's like it has multiple dimensions, right? Because it's a cross product. So yeah, so I guess how do you define a subspace in multidimensional spaces? That's the first question. And then second, how do you finish the proof to show this? Is a second question. And,
Okay, I understand your problem. Actually, the open set in AR in the subspace topology of A alpha is like this. It's like this. A alpha intersects with U alpha. It's not A alpha itself. So basically, we're proving. I'll show you my proof. Oh, wait. Okay. So we have to intersect with this, which is open set in the products in here, right? Intersects with this Cartesian product of A alpha.
yeah, okay, so that was the thing I was asking for, I guess, is so here you do an intersection, right? But you do an intersection of like multiple dimensional things. So if you're familiar with vectors, so basically you're kind of doing an intersection of two vectors. And my question is, did we ever define a multidimensional intersection?
Oh, I'm not. I don't know this.
Because I don't know about it, but then because without a definition, I'm not sure if it makes any sense.
Okay. I don't know the answer of this.
Yeah, well, I guess what you did is correct. I'm just not sure if we ever did it before, like the definition and stuff. Well, let's assume we defined it that way.
Oh, sure. It's the easier way. Just assume it is correct.
Because I think it should be right. I just don't think we ever wrote it in the book or made a definition like that. So I think that should be clarified. Theodora, Zigan, should we go on? Should we pause? Should we repeat something? Talk to us.
Yeah, do you have any question about this proof? Except that one.
Sorry, I just well, I was just go off for a while. So what is your question? Could you repeat that?
So I think my question was, so basically in this proof, what Holly and I was both thinking about, that you have to do this, like intersection, to prove this, right? And then it proves this statement. But this is like a multidimensional thing, right? Because that's a cross product, right?
Exactly, but what you can do is, but what you can do, you want to show this equation, right? You want to show the right-hand side equals the left-hand side, right? Well, if you want to show that, what you need to do is, again, try to show it by checking by definition. This is a set theory problem, right?
Yes, it's just, it's just, I think we never ever defined an intersection of multidimensional like vectors.
Well, we don't really define this kind of product equation, but what we really define is, well, suppose you have two sets, then of course you can define the intersection of these two sets, all right?
Oh, we defined it as they have the same element, so we just have to prove that if they have the same element, this element would look like that. Oh,
exactly.
Okay.
They are both a subset of this product of everything, right? Product of pi x alpha. So of course, you can define the intersection of two subsets of this pi r x alpha, right?
Mm-hmm. So I guess we just need to add a couple more lines below of why this equality holds. But yeah, makes sense.
Yeah, if you have an element on the right-hand side, then this element must be on the left-hand side and vice versa. And it's also okay, right? So yeah.
Sure. Should we leave it as an exercise? Should we go on? Should we try to do it together? Thoughts, comments?
You can write it here, like your thought here.
Sure. I'm just not sure if you want to spend your precious time on that, right? Because you have a lot to cover. Oh, you can just leave it as a proof if you want. I don't think it's hard.
Okay. And I only have three theorems left. Then I'll go on here. Oh, okay. The theorem 4 is in the Hausdorff space. If each space X alpha is a Hausdorff space, then the Cartesian product of X alpha is a Hausdorff space in both the box and product topologies. This one should be easy.
I forgot definition of a Hausdorff space.
Oh, okay,
What
okay.
was it?
I'll write it here. It's simple. Like if we have 2 points X and Y, which is different, and then we can find in X, in the space X, and then we can find 2 open sets, U in X, U containing X, and then V containing Y, which U and V does not intersect. Like U intersects V equals to the empty sets. Oh, terrible writing. Hope you understand. This is U.
So you mean that for any X, Y, you can always find 2 non-intersecting? Okay. So basically, like if you have 2 points, you can always draw circles around them so that they don't intersect. Okay,
Yes.
that makes sense.
Yes.
Sure. Well, I guess we can just do the completely same thing. Like we can take 2 elements and show that in different their different coordinates don't have like we can always find non-intersecting like subspaces, and then we take their cross multiplications and we use the formula that we just did on the last slide. I think that should be it.
Yeah.
I think we should give a little bit of time to Zikhan and Theodore to think about it. Zikhan, any thoughts, comments? Just say something. We miss you, you know? I didn't see you for half a year. Well, maybe any, hey guys, any noise? Make some noise. Because I think, I mean, Holly knows the proof and I think I know the proof. So we just need to make sure you know the proof and then we can go on. So.
Okay. Oh, before I show my proof, I'll give a little explanation on the 2-dimension space. So here, if this triangle, this rectangle have x, this open interval x in the, for example, u in the x coordinate, and then a v in the y coordinate. Then we can find another rectangle which has the same x coordinate but different y coordinate. For example, it's w, and these two are disjoint, right? So all we need to do is to find at least one coordinate x alpha, which is different from y alpha, for the 2 points x and y in the product space. Then we can prove that, and then we can find, and then we find two open sets containing them, and then they're disjoint. Then we prove then it's the proof, right? So I'll show you my proof. Wait.
Oh wait, actually, the gun said he wants to sync, so maybe we can wait a little bit.
Oh, okay.
I'm not sure.
Sure.
I just remember what we discussed in the 17th, where we discussed the product of two Hausdorff space is a Hausdorff space, and I think maybe the proof is similar, but I don't know how to like write very like in this chapter how to write it. Yes.
Well,
Yeah,
how
this
about
is
we
something
draw?
you should try because writing in this topology language is slightly different from what we've learned in algebraic or in analysis. Okay, so which is something you should practice.
Yes.
We can write here, and we can all see it.
So first we need two distinct points maybe. So how to write it? Okay. Can we write it this way? So if each space is a Hausdorff space, maybe in this one, like they both belongs to a Hausdorff space X alpha, and because it is a Hausdorff space, we can find two neighborhoods, maybe U1, maybe U1 and U2, where they are disjoint, and so these two.
Yeah, exactly. Like we just need to find one coordinate that are not the same, then they're disjoint, right?
Yes. Then little confusing here. On this point, maybe belongs to some like just this one. This belongs to some. Maybe another product topology or box topology, and their intersection are disjoint because this U1 and U2 are disjoint. I don't know.
Yeah. Or just write this X alpha into and change it into U alpha, and then you have a better thing. Because it's open set, right? You don't need to write X alpha. You just need to write it in like the basis as the basis form.
Yes.
Okay, then I think you get my idea, and I'll show you my proof. Okay, here. So all I do is just find one coordinate X alpha, which is not equals to Y alpha. And given that all the space X alpha is a Hausdorff space, then we can find a U in open in X alpha, and then V also open in X alpha, and then this U and V is disjoint. So this product of U beta and then the product of V beta are disjoint because and we can because they have one coordinates which are different here. These are right because this U and this is V, and then and then there are some like some U beta and V beta are the same, but because we have already find some U and V are not the same, then this whole things are disjoint. Do you have any question about this?
Well, I guess we can go on.
Oh, okay, great. Then I'll go on to the next page and slide. Oh, okay. So this one is a little bit difficult. Let X alpha be an indexed family of spaces, and let A alpha in as a subset of X alpha for each alpha in J. And the product space of X alpha is given either the product or the box topology. Then the product of the closure of A alpha is equals to the closure of the product of A alpha. A little clues, we can use like prove it in two directions. One is here and one is here. And there's a useful theorem we can use in the chapter 17. Do you need some proof, clues? Or
Well, I think I have an idea, so
okay.
I'll try to bear it till the end. But yeah, maybe we can do it together, guys. Like, how about we start with a first direction? Maybe we can use a definition, for example, like I think definition of the closure of a cross product of A's, it would be intersection of all open subspaces which contain that cross product of A, right? So I guess, yeah, so I guess, I mean, this would be equal to intersection of all, say, U, like, I don't know, U betas, and those U betas, they contain the, oh, sorry, the cross product of A alphas. So this is by definition, right? And so I guess what we can show is that if they contain that cross product, then oh wait, and from this side we have this just equal to a cross product, and here you have intersection of all I don't know, whatever, some kind of sets which contain, for example, A alpha, right? And so this just happens for all of the dimensions, right? Oh, actually,
like the closure is the intersection of all the closed sets, right? But U beta is
of the no, wait, of the closed. Oh yeah, you're right, of the closed. Yeah, thank you. Closed here and closed here. Okay, sure. So then how do we go about it? Well, I guess we can use our definition that we had before, that an intersection of these two well, sorry, here should be this actually. Yeah, so I guess intersection of this two would be cross product of intersection of, say, U1, 1, U2, 1. Right. So, well, you get my idea, right? So basically, the intersection of two cross products would be equal to a cross product of little intersections, right? And so if we write it in this fashion, we get that this intersection of closed sets would just be equal to a cross product of intersection of closed sets. And so we come to this thing, I guess, right?
Oh, okay, let me check it because it's not my way. I'm sorry, which side is the left side? Like, which side is the product of the closure?
Sorry, what?
Here in your writing here, is this one equals to this one?
So I think basically what happens is, so this one is equals to this one, which is, I just rewrote it by definition, and then I used I use this equality, that intersection of two cross products is a cross product of intersections. And so I rewrote this as this, and then I realized that this is just equals to this, and this is equals to this. I hope that probably should be it, I guess.
But in the previous theorem, we used the open sets, but if it's a closed set, I'm not sure whether it also works.
Oh yeah, what the thing is that the equality that you wrote, I think it doesn't matter if it's open or closed, because just is good for all sets, I think.
I see. Okay, so yeah, it might be a proof. I think it's also a proof. But my way is is a lot difficult. Oh, okay, I'll show you my way. Here. So I use this theorem in theorem 7.5, which means X is in the closure of A if and only if every open U containing X intersects A. So it means that if X is in A, then in the closure of A, then the U intersects A will contains a set, a point, for example, a point Y intersects A in the S of Y. Oh, too bad. Then we can find, yeah, like this line. We can find a Y alpha in the intersection of U alpha and A alpha for H alpha. And so so this point Y is in U and also in the product of A alpha. So the arbitrary U intersects with it's arbitrary U containing X. It intersects with the product of A alpha is not empty, and so we have X in the closure of products A alpha. Here we assume X is a point of this, right? We assume X this condition. Suppose this condition and we prove this. And then the other direction is assume X is in the closure of product A alpha. And let V beta be an arbitrary open set of X beta. This beta is just an index. It's just the name of the index. And then since the inverse projection V beta is open in the pi X alpha in either the box topology or the product topology. So this whole intersection is not empty. Then we have this, and then we can find the point Y as the element of this intersection. And then this Y beta is in V beta intersects with A beta. And this follows that X beta is in the closure of A beta. So X is in the closure of the product A. Product A closure. Oh, it's a very difficult problem, a difficult approach. So I think yours is better. If it's correct. Do you have any question about this approach?
No, but let's ask Zikan and Tudor. Well, maybe we can go on then.
Okay, then we'll go on. The last one, the Theorem 6. First, we have the function f from a to the product x alpha be given as fa equals to f alpha a. This f alpha is this fa is the stats of many functions. So one of the function f alpha is a to x alpha for each alpha in J. So let this product x alpha have the product topology. Then the function f is continuous if and only if each function's f alpha is continuous. We can also prove this in two directions. And this theorem is very important because the box topology doesn't have the same property, which makes this product topology a better topology than the box topology.
Okay, then, well, I think we should start with the definition of continuous, right? But I only know the definition of continuous in analysis. Is it the same in topology or is it different? Oh wait, it should be different because it doesn't have metrics, right?
Okay, I'll read it for you.
Oh, is it when you have like the if output is open set, then the input should be an open set?
Yes, exactly.
Oh, okay. Well, let's start with one of the directions, I guess.
Okay.
Probably you can be like, if f is continuous, it means that for any open set u in, say, yeah, like this. Oh no, sorry, for cross product, yeah. Then for any open multidimensional thing in the cross product of x, it should be that f minus 1 u is open, right? And that's just a definition.
Yes.
And then what we have is, I guess, that basically means that I think we have a definition that if it's multidimensional, it means that f1 minus 1 u, let's call it u1, f2 minus 1 u2, and stuff, right?
Mm-hmm.
Where u1, u2, blah, blah, blah is just u, right? So basically this is open, and this is also open. And so what we get is that this condition implies that if something is
if you write it in the composite function, it will be easier to.
Well, I don't think there's difference. It's a notation issue. I'm just trying to see how to make it like logically rigorous, because if you get from here to here, then it means that this this direction is implied, right? And so it means that this part would be open. So and this was open by definition. So I guess then this arrow implies that this happens for each of the lines, right? So it happens for all the alphas. And so you get that this is continuous for all f alphas, I guess. I'm trying to see if I have any logical mistakes in here, but I hope not. And I guess you can also do it like, you can always say that U can be any open set. So you can always take any open coordinates of it, so you make them independent. So I think that should work. Okay, I hope it works. Any comments, Theodora, Tika?
Like, do you have any idea how to prove the second direction, the other direction?
Well, I guess it's actually the same, because if you have that for any open set, if you have it for any open set U1, f minus 1 U1 is also open, and then this happens for all alphas, right? Then basically nothing stops you from putting them into a cross product. So basically what happens is that you know that because all those are open, then U is open. And because all those are open, then F is just F minus 1 U is open. And what also we have to, I guess, say is that this open U is any open set, but we can make it up with just choosing specific open sets in here, so it still works. Yeah, it should be it.
Yeah. It's basically the idea you get. I'll just show you how to write it in the proof. Oh, in the language, in the math language. Okay, so in the first direction, I have like construct another function pi beta, which is which is the projection map pi beta, and then f beta is the composite of pi beta to nf, and since this pi beta and f are both continuous, then f beta is continuous. Here, if we first assume f is continuous, then this f beta is continuous for every beta. And for the other direction, if f alpha is continuous, let me show you why pi beta is continuous. So if we find that u beta in x beta, open in x beta, then this thing is a basis, as a sub-basis element for the product topology, right? That's how we define it. And because it's a sub-basis, it's open on x alpha. So this pi beta is continuous. And then we get the first direction. The second one is we first assume that f alpha is continuous. And then this composite function is the same. And then the more important part is here. Because this thing is a sub-basis on the product x alpha, and it can, and if we write this function into f beta minus 1, we get f beta minus 1 in u beta. And this u beta is open in x beta. And because we have assumed that f alpha is continuous, which this whole thing, f beta minus 1 u beta, is open in A. Right, because A is this domain. And then so left-hand side is also open in A. Then we prove f is continuous. Okay. Do you have any question about this?
Well, I don't have it.
Then should we go to the next question?
Sure.
Okay, then I'll check. I'll go to the next slide. Oh, okay, so this is actually an example which shows us why the box topology is not as good as the product topology. Let's consider the R omega, which this where each R has the standard topology and R omega has the box topology. So it's actually an infinite times of R. And then we define a function f from R to the R omega by the equation ft equals to t. And then fnt equals to t. So the function f from R to R omega is continuous for each n in the natural number. So we need to prove why when it is given the box topology, it does not work. This f is not continuous.
Well, the difference between box topology and product topology when it comes to infinite dimensional spaces is only that I think box topology is a little bit more finer, right? Maybe
Yes.
because it's more finer. Well, let me think. So something that is open in the product topology may not be open in box topology, maybe. I don't know.
Yes. Like the inverse of the like open set is not open.
Yeah, because the inverse, because it's basically this function, like inverse is just equal to the function, right? And so, well, but it doesn't make sense. That doesn't make sense, right? No, actually, it should be open, because if your T initially is open in no, that doesn't make any sense. Because
I have
say,
to admit that, yeah, I don't quite understand this answer. I have already watched many videos about this, but I still cannot understand it very well. So if you have any ideas how to prove it, I'll be very happy.
because because the thing is that, okay, in the box topology, say, but you still have the same conditions, right? So in the box topology, you would just have a cross product of those R's, and then what you have is, say you have an open set in RW, and if it's open, it means that it's just T, which is open, right? But, and then it means that all of the sub functions would be continuous, and then, no, that, I think it also should be continuous. I don't think that there should be any difference. Like really, because like if, oh, Professor, you're saying anything? Because you're very, we can't hear you.
Oh, I'm sorry, I didn't say anything. No, but yeah, you should think about this problem, right? So it is continuous under this product topology, but it is not under this box topology, right? This is one of the reasons why we don't want to choose a box topology, because sometimes it makes something weird, like this kind of function is not even continuous.
Wait, can you say it again?
Well, I say this is one of the reasons why we don't want the box topology, or the box topology is not a very natural or not a very good topology. It's just simply because, well, for instance, this kind of function, it seems to be a perfect function, but it's not continuous. And
Wait, why is it? It's not continuous.
Yes, it's continuous on the product topology, but it's not continuous on the box topology.
But why?
It's not continuous on the box topology.
No, yeah. I'm just like, I'm asking, why is it not continuous on box topology?
Well, because well, our textbook just have a very good example of the inverse of an open set on the box topology is not open in R.
Yeah, like
right?
this one.
Exactly.
But I don't understand this line, this inverse. Why is it equal to 0?
So what kind of what kind of element or what kind of x or t can give you an element in B? What kind of t such that ft is belongs to B?
Oh, so basically you're saying that bases like this can only cover one element, which is 0?
Not really, not about the basis. So you can see that B, this set, well, this B, minus 1, 1 cross minus half half cross minus third third, and so on. This B is actually an open set in the box topology, right?
Oh yeah,
So
but
its
input is 0, so it's not.
But if you take the inverse, if you take the pre-image of this set B, you can find that, okay, the only T such that Ft is in this set, if in this Ft is in this B, only contains one element 0, right? Otherwise, F something else, for instance, F.1 is not in this B. F.2 is not in this B, right? F1 is not in this B. So the only element such that you can guarantee that F this element is in this B is 0. Only one number in the F inverse B.
Okay, but then why is it continuous in the product topology?
Well, it is continuous in the product topology. Why is that? You can also show that. I think this will be an exercise for you. Try to show it.
Because this is not infinite for the product topology.
Oh, yeah, because you have a, oh yeah, sure, that makes sense.
Yep, but I still have a question. Why is it all T, but here is different?
Well, you can, well, first, this notation you have is wrong. It should be F inverse B, it should be -1, 1, intersect with -half, half, intersect with something, right?
Oh, yeah.
Right?
Sorry.
So yeah, so why F inverse B should be this? Because you can see that, okay, if you want to take the inverse of B, then that means if you want some element in F inverse B, for instance, T, okay, T is in this F inverse B, then what you have is, okay, Ft is equals to T, comma T, comma T, comma T, right? Always have T. Then this T must be in this -1, 1, right? If you consider the first component. And then if you consider the second component, it must be in -half, half, right?
Yes.
And then it must be in -1/3, third, and so on, right? So it will be, it must be in all these kind of open intervals, minus delta, -1/n. Then, well, what kind of numbers satisfy this condition? The only number that satisfies this condition must be 0.
Okay. So T is not equals to -1, 1. It's just in -1, 1.
Well, T is a number, right? F inverse B. What is F inverse B? F inverse B is a subset of R. You see, F is from R to R omega. So which means if you want to see the pre-image of a subset of R omega, it must be a subset of R. So you must check what kind of what kind of element, what kind of numbers are in this set, right?
Okay. Yeah. Thank you. Okay, then we have the last question left. Or do you want more time to think about this?
I'm good. I got it. Let's ask others.
Okay, then we'll go to the next slide. Okay, this is the exercise 6, which also tell us some difference between the box topology and the product topology. So let x1, x2 be a sequence of the points of the product space, product x alpha. Show that this sequence converges to the point x if and only if the sequence pi alpha x1, pi alpha x2, this pi alpha is a projection map, and then converges to pi alpha x for each alpha. And then, is this fact true if one uses the box topology instead of the product topology?
Okay, sure. So I don't think I remember the definition of convergence in the topology. What was that?
I think it's very similar to the analysis. Oh, let me check it again. Sorry, wait a minute. So if it's convergence to a point X, then for any n equal bigger than the capital N, every point is in the open set containing X, containing the point X. So
Wait, can you say it again, please? So the limit point is
X, for example, and then we can find a neighborhood U containing X, and then for for example Xn, when n is equal
for every open set, there always would be another point from the sequence, right? Okay, sure.
if there's only one point, then this X is the point. It's itself. The limit is itself. Xn when n is bigger than n, then all the Xn is in the U containing X. This U is a neighborhood of X.
Well, I guess we just do the same thing again. We kind of take any open space around the point X, and then basically what we see is that it should always contain some other point, right? And that because it contains some other point, we look at their coordinates and we get that B alpha x1 is also contained in there. Well, let me just write it. It's hard to say. Sure. So basically, I guess if for any open set U which contains X, there exists some Xi in that U, right? So we have this, which means that the sequence converges, right? That's a definition. And then basically what we do is we say, okay, great, then it means that Xi, which is actually like a little vector, I guess, which is P1 Xi, P2 Xi, and stuff, is inside of this open vector, which is also just some U1, U2, U3, and stuff. And that means that this is inside of this, and this is inside of this, and this just happens, and then basically this is the same as us saying that that the sequence converges for this once, right? And so the other direction is just basically very similar. You have all the sequences converging, and then from these sequences you just build them together into a vector, and you get this statement, right? So I think that should be it.
Yes. Are you saying for product topology or the box topology?
That's oh my gosh, which one? Oh, box topology, right? Because box topology is allowed to be. Oh wait. No, wait. I'm getting confused all the time between them.
Like the box topology has all the for infinite numbers, all of them are open sets. But for product
Oh
topology,
yeah.
there are finitely many indices.
Yes, there's finally many non-trivial places. Okay, I guess that I'm not sure. I don't remember anything that restricted the. Well, no, yeah. I guess no, really. I don't see that this proof would be different for any of them. But I may be mistaken.
Like from the left to the right, these two are the same, but for the other direction, then box topology and the product topology are not the same. If you write it in the math language, we have this. We need to find an n which is bigger than all the the max of all the indexes. Oh, it's too difficult, right? For n1 to n2, all the way down to infinite number for the box topology, but it is impossible to find the max number for an infinite number, right? So we cannot find an n that suffice that n when n is bigger than this capital N, it converges to a number x. But for the product topology, because it's not infinite, we can always find an n. So we can prove that it's converged to x.
Oh yeah, sure.
Converges to x. Okay. Oh, I'll just show the proof here so everyone can read it. Oh, can you see it? There are many words. Oh, sorry. This is from left to right, and here is from right to left.
Okay, sure.
Okay. Then my part is finished.
Very good. So you can see that. Oh, thank you. So you can see that you guys can see that why in general we would like to prefer the product topology instead of the box topology, right? Because for the as we learned in the calculus class, a continuous function must be componently continuous. But this is only true for this product topology, not for the box topology.
Mm-hmm.
Okay, sure. Then if that's all, I'll probably start with a little bit of my part, but then we only have half an hour left. So I'll continue next time the rest, which I would have. Give me a second. I'll open my notes so I can look somewhere, and I'll make the whiteboard.
Do I need to stop?
Yeah,
sharing?
can you please stop? Yeah, can you please stop sharing the whiteboard?
How can I stop?
I think you go up and you just click stop. Or maybe you click down. I don't know.
I have already clicked stop.
I think you have this stop sharing. On the bottom column, there is a share or stop sharing, right?
Okay, I think I have stopped now.
Okay, great, thank you. And let me share. So By the way, this should be open to anybody. So I think if you guys have any questions at any point, you can just always, feel free to like write or scribble anything here. Sure. Then let's just start. So today we're going to talk about metric topology, and metric topology is awesome because it's so useful and so nice, right? Because what we were doing so far before, we were working with very like abstract things which didn't have a specific size, and now we want to measure that size, right? And so to do it, we have a lot of different ways to measure sizes and distances. So say, for example, if I take a metric, and I would define it like this. So, a metric is a function, we call it d, from x cross x to r, right? And x is just a set on which we define the metric. And so why is it x cross x? Because you'll see then that it looks like this. dxy, first property, should be bigger or equal to 0 for all xy in the x, right? And the equality holds only if you have x equals to 0. So basically means that this is equivalent to dxy equals to 0, right? So let's look at this property and analyze it. So we just want a distance. So of course we always want a distance to be positive or at least 0, because negative distance doesn't make any sense to us specifically, right? That's why it's non-negative. And of course we don't want distance to be 0 if the points are not far apart, right? So I think so far this is very logical, right? And then, oops, give me a second. The second is that you want dxy equals to dyx, of course, for any xy in the x. Why is that important? Because we don't want to struggle with orderings, right? Because it's not a vector. What we care about is only the distance. We don't care which direction it goes to, right? So that's the second property. And then the third property is that a triangle inequality. This is like super important for analysis, and analysis had a lot to do with topology, so it was very important in topology too, I guess. So dxy plus dyz is bigger or equal to dxz. So what does it tell us? So say if you have a point x, you have a point y, and you have a point z, what it tells you is that going to here and going to here totally would be longer than this. And of course we want that to be true, because in a universe where this doesn't hold, that would be a very weird universe and it would be really hard to work with, right? So of course we want that property. But except for that, metrics can be just anything. If it holds its two properties, you're good, right? And so we'll look later at different kind of matrices, right? But let me first like explain you one of the basic definitions. It would be BD x epsilon. So what this ugly thing is for epsilon, which is non-zero and just positive, epsilon usually are some small numbers. You have this defined as a set y such that dxy is less than epsilon. So what does it tell you? It's basically just a set of all points for which the distance to x is just less than some specific constant. I see something in the chat. Give me a second. Oh, okay. You can see now, right? By the way, just feel free to speak up because it's hard for me to see the chat when I'm sharing the screen. Okay. So basically, we have a point x, and then everything that goes distance of epsilon or less would be in the set. So for example, like if we have R2, that of course would be not a circle, but kind of like a plain ball, right? Because it takes everything inside too. If that's a 3D, it's just a ball. If that's a 4D, it's a 4D ball and stuff. And so usually we call them E ball centered at X, right? And this D basically means that we're using a specific metric, which is a D metric, because for a different metric, this ball would be very different, right? And I'll show you the examples. Yes, but just a little bit later. So first, before I show you the examples, we also would have to define what is a metric topology. So a metric topology, which is a nice thing, is just a topology which is induced by D. Induced by D, meaning that you're using a specific metric rules defined by D. It's a collection of all epsilon balls centered at X from X and E within 0. So basically what it means is that, say you have a specific set X, right? And then you have all kind of elements in there. You have all kind of epsilons, and so and of course you want this ball to be inside of this metric, right? Okay, and so basically what happens is that all those balls around those points would be a collection which later would be your basis, right? Which you would base your topology on. And of course, they don't have to be on a similar size. Okay, and how do we prove that it's a basis? Basically, what we do is, let's first remember what is the definition of basis. And so the first definition of basis is, anybody wants to help?
Sorry,
go on.
What question again?
Can you remind me the first the first property of a basis?
Oh, like every elements or points in the space can be like is in the basis.
Yep, sure. So basically, what it says is that for every element X, there should be some ball which covers that X, right? Because if you have a point and it's not covered by a basis, then your base is not doing a good job. And so, okay. And I think that this is easy, right? Because what you just do is you specifically define a ball centered at X. And then for any non-negative epsilon, of course, your X would be inside of that ball because you center it at the X, right? So this property is done. It's easy. And then the second property is a little bit harder, but still not. Basically, it means that if you have a basis 1, which contains X, and you have a basis 2, which contains X, you have to have a basis B3, which is contained in the intersection of B1 and B2, and then X is in this B3. Right, can you see, like here? I hope you can see. And so why is that true? So let's look at a specific thing that we have. Imagine that you have, well, of course you have your set X, but then you have a specific point X in it, and you have a ball around X, right? With a distance epsilon. And so you have another point Y inside. Of course, we understand that we can always define a small enough ball inside so that it's inside of our basis 1. That's our basis 1. And we want a smaller ball, sorry, inside of the B1. And so what happens is, how do we rigorously show that there exists HB3? Is we define it to be centered at Y with a distance which would be epsilon minus distance xy, right? Or something smaller. Why? Because if you look closer Here's your x, here's your y. This is a diameter epsilon. This is a distance dxy. Of course, if you make the ball of this radius, it would stay inside of a bigger ball. That's why it will be completely inside, right? So we know that this is inside of the B1. Does it make sense so far?
Yes.
Great, because I think that like what actually is said in there is really easy and really intuitive, and you all know that. It's just the notation is kind of ugly, so you have to get used to it. Okay, and so why is that true? Is because of course for any point z inside, what happens is your dxc is less or equal than dxy plus dyz, and this would be equal to, let me write from here, dxy plus alpha minus dxy, of course it cancels, and you get alpha. Oh, wait, sorry, epsilon. And so why? Because we specifically defined this to be this, right? And so now it nicely cancels out, and we have the distance between x and z would be less than epsilon. So what we just proved is that for any point in this smaller ball B2, as far as it stays inside of the B2, it would stay inside of the B1. But you also can see it from the image, of course. Okay. So that was our stuff with balls. And so how do we prove the second condition of basis? Is that, see, if you have a specific element x, and it's in one of the bases B1, and it's in the second basis B2, of course, you can always take a basis that is centered at x, and because we just proved that you can always choose a distance so that it stays inside of this ball, and then it stays inside of this ball, we can of course make it so small it stays inside of their intersection, right? And so we just define it to be B3. So we just found a B3, which is inside of the B1, intersect B2, and B3 has X. So that was our second condition we needed that to prove that it's a basis. So yeah, we just proved that the collection of balls with all kind of radiuses centered at the point elements of our set is a basis for the topology induced on X by metric D, right? So great, it means that we can operate with those balls and use that as our building tools for our topology. Okay, and so basically what we do now is we say, what happens with our definition of an open set? So before U was open, if it is contained in the topology X, right? How can we rewrite this, but now with our definition of metrics? And so a set U is open in the metric topology induced by D, if and only if for each y in the U, there exists some delta bigger than 0, such that BT y delta is in the U. So basically what it says, if you have an X, U is considered to be an open set in the X if for any element of the U, there is always a small enough radius such that there is a ball which would be with this radius and it would stay right inside of the U, right? So yeah, we now just have a much nicer definition of an open set, and it's very understandable, right? So metrics make everything much easier. And so now let's just look at all kind of different matrices. Well, I guess I'll start with the one you know, right? So for example, the usual one which we use all the time, dxy equals to x minus y. This is simple, right? You take, I don't know, you take a line, you have a coordinate 1, you have coordinate 3. Distance between them is just 3 minus 1, right? So it's 2. And so it has all properties of matrix, so it's a distance, you know it. It's great. And of course, you can do the same, but with vectors. With vectors, you have norms, right? Like the one that we usually do, like you have a vector like 1, 3, then you usually do square root 1 plus 3 square and stuff, right? So and then you can make a norm of u minus v to take distance between vectors, which is the same. So those all things you know from your calculus class and stuff. There are a lot of other metrics you can even come up with yourself, right? And they can be useful for all kind of things. So, for example, you can make a matrix with the xy equals to 1 if x is not equals to y, and the xy is equals to 0 if x equals to y. Okay, so this is a very interesting metric. Why? Because you have all kind of points, and this is a distance 1, this is 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 1. Everything here is just 1, right? But I guess this is important metric. I guess it would be important, say, in programming maybe, like stuff like that, right? Because it's very discrete, because it only uses integers, and there's only 2 states. So it's a simple metric, but it works. So why is it a metric? First is that all of its values are non-negative. Great. Second is that inequality holds only if they are equal. Then also what happens that you have triangle inequality, right? Because say if you have the xc plus the zy is less, here then the xy, why? Well, because basically what happens is if those two things, this is just maximum 1, right? And then what happens is that if like this are either 0 or 1, right? And if it's 1, we already win because this sum would be bigger than 1. And if it's 0, it means that x equals to z. But then because x is not equal to y, right? Because it's 1, we know that this is just x, y. So this is actually the same things. And so, yeah, so you still get the inequality. So we prove it has triangle inequality. And then what we also can see is that dxy is equals to dyx. Why? Because if they're equal to each other, they're both 0. If they're not equal to each other, the distance is always 1. So yeah, it stays the same. Great. And so, okay, yeah. We also can see that, for example, the order topology, AB, is a basis element for symmetric topology. Why? Because this can be written as this, where x is just a plus b divided by 2, and epsilon is just b minus a divided by 2, right? Yeah, so basically you can see that we always were using the metric topology when we use the intervals. We just never actually said it out loud, right? Okay, and so if x is a topological space, x is said to be metrizable. What an ugly word though. Metrizable if there exists a metric D on the set X, which induces a topology. So there exists a metric D on set X, which induces topology on X. Sorry for my handwriting. And so yeah. So as you can see, not all sets can be metrizable, which is bad, because it means that it's harder to work with them. But a lot of nice sets are metrizable, so that's good because we know more about them, we can quantify them. Okay, and so what we want is we want to know which conditions on a set lead to it being metrizable, right? Because we would want to know that, oh, the set has this and this properties, sorry, and because it has this and this properties, it is totally metrizable, so we can always have a metric. And so, but we will do that later in chapter 6, and we'll come to it back. But now we'll just keep on doing our thing, which is groundwork, right? And so, okay, another definition is a subset A of X is said to be bounded. So A subset of X said to be bounded if there exists some M for which the A1, A2 is less or equals than M for any pair of points A1, A2 in the A. So basically what it tells you, if you take any pair of points and the distance between is always less than M, then of course the entire set is just bounded. And you can of course see why bounded sets are nice. And you can learn more about it when doing analysis. So basically, metric topology has to do a lot with analysis. You can also define diameter, for example. Diameter of A is a supremum D A1, A2, A1, A2 from A. So what it tells us that, okay, if somebody forgot what supremum is kind of like a maximum element. It's just, we cannot say maximum because in some sets there is no kind of maximum, but there is a limit to a maximum. So this is kind of like an upper bound limit. Yeah, and so it means that you'll take the closest number which approximates the distance between the points and which is the maximum from O, right? So basically, if you have a set A, probably these 2 points would be the farthest from each other, so that would be your diameter of the set A, right? Okay, great. But still, those things are mostly like closer to analysis, so we're not put too much effort on them. But what we have to know that there are a lot of cool tricks with matrices that you can do, right? Because say if you have specific unbounded sets, then definitions of metric can be really bad because, like, imagine you have points which are infinitely far from each other, right? And you don't want that. Because that would make your work with matrices meaningless, right? You don't want the distance between this just be infinity or whatever. And so to get rid of all kind of bad stuff that we can have, what we do is we define a specific metric. So if you have a metric D, there always exists a metric D conjugate, which would help us in this following way. So D conjugate xy is is equal to minimum.
By the way, so I think here you better pronounce it as D bar. Conjugate is something special, something
okay.
special. Yeah.
Sure. D bar. Okay, so D bar is a minimum from dxy and 1, right? So basically, whenever this distance between 2 points is less than 1, then we just write it as a distance. But whenever the distance between 2 points go larger than 1, we just write 1, right? So you can think about it visually as if you had, for example, like points that were really far, and what you did is everything that was outside of a specific circle with radius 1, you put it into your circle, project it kind of. So I think it is a lot nicer to think about it in terms of projections, but that's just how I like to think about it. Why this is a metric? Well, let's recall 3 properties of metric. First, it has to be non-negative. Is it non-negative? Yes, because if you recall, it's a minimum of dxy and 1. This is a metric, so it's always non-negative. This is a non-negative number. The minimum should be non-negative. It's always non-negative. Also, d bar yx would be minimum from dyx and 1. If you recall, this and this are equal because this is a metric, and so the minimum from them would be equal, of course. So this is equal to d bar xy. Second property done. And then the third property is the triangle inequality. Right, so basically you have to prove that d bar xz is less or equal than d bar xy plus d bar yz, right? Okay, and so you have to prove this triangle inequality. How about you try to prove it yourself, guys, because I just want to see if you got the previous parts, if you know how to work with it. Okay?
Yeah,
Hello?
I think, yeah, can you hear me?
Yep.
Oh, okay. So if the d bar is the smaller element is 1, then 1 is smaller than 2, right? Let me write it. And then if it's not x, y, and z. So if let me write it here. How can I write?
I think what you do is you go up and you comment or something.
Yeah, x, and this is y, and this is z. So if an x and z is the dxz is bigger than 1, then for if this one is 1, for example, if this one is 1, then we have to prove that this yz is also bigger than 1. Right. Right. Then we have proved it already.
Ooh. Okay, I see. So you're saying that if the distance between y and x is big, and between x and z is big, then it's totally bigger than yz. So you have proven it for that case, right? What happens? What happens if, for example, d bar xy is very small and d bar yz is very small?
But then for the triangle system, like if it's only d, then this 2d here definitely is bigger than this d. Right.
Why?
If they are very small.
Okay, so how about I rephrase what you just said? And
Okay.
yeah, so what you said before is, oh wait, where is, where did my thing go? I think I cannot write this. Oh no, yeah, sure. So basically what you just said is this at maximum is 1, right?
Yeah.
So if this or this, whatever, is bigger than 1 or 1, the inequality holds. The only problem is then when we don't know what is that, but we know that both of them are small, so both of them are less than 1. So we have to prove this inequality for that case, right? But what happens when both of them are smaller than 1? What do we know about it?
Like it's the standard metric, right?
Yay!
It's
Great. Then we just write it as dxy plus dyz. And because it's a standard metric, it already assumes triangle inequality. So it is bigger than the xc, right? And so that's great. Because basically, what happens is that this thing cannot be 1, right? Because if those two things are smaller, then this is totally smaller than 1, and because this is totally smaller than 1, this would be smaller than 1. So we got inequality. Great. Let me see how it's actually 8. So this, I don't want to hold you more, guys. And we've done quite a bit today, and we can just continue next time.
Okay, thank you.
Okay, thank you. Thanks, Holly, and also thanks, Aya.
Hey, you're welcome. Then are we meeting next Friday, the same time?
Yeah.
Yeah.
Okay, great. Then see you next week, guys.
See you next
you.
week.
See you next week.